All right, I think that's enough of the basics and the mathematical idea behind what we're doing. Let's take a couple of looks at examples of how you might apply this. Because we haven't changed anything about how we're dealing with position and velocity and acceleration, all that kind of stuff, all the rules work the same way, whether it's in 1 dimensions or 3, which means that for constant acceleration, notice I'm writing acceleration here as a vector to keep in mind that these equations we're about to write require constant acceleration, not just constant magnitude of the acceleration. Acceleration is a vector, and it's only constant if both the direction and magnitude of the vector are constant. So in other words, if the entire acceleration vector is a constant value, then we can use those same kinematics equations we've been seeing before. That is, the velocity at any point is equal to the initial velocity plus the acceleration times the time. Just keeping in mind that now these are all could be multi-dimensional vectors, but they still work the same way. Another one, now this time rather than using x or y or z for my position vector, I'm just going to write r, keeping in mind that r accounts for all the different options, x or y or z or some combination thereof. And finally, now so these are both vector equations. The last one you have to be a little bit careful of. Actually, in fact, we're going to leave the last one for a second. We're just going to look at these two for the moment. These two are full vector equations. The reason I say the last one you have to be careful of is that you can't square a vector. This is bad. If you ever find yourself starting to do it, don't. So we're going to come back and look at how to deal with that one in a second. For the moment, let's look at these other two, because these are just full-on regular vector equations that work in 1, 2, or 3 dimensions for constant acceleration vector. And this might look like anything. Let's say we have one of our examples that we've looked at a couple times. Here's the Starship Enterprise, and it's moving with some initial velocity vector that is 30 I hat plus 40 j hat meters per second, where the I hat and the j hat in this case are just, x and y relative to some arbitrary plane. And let's say that it fires up its engines, but it's pointing its engines a different way to try to cause some constant acceleration vector represented by -2 I hat plus 2 j hat over and to the left. In other words, it's moving up and to the right, but it's firing some rockets up and to the left because it wants to change where it's going a little bit. And then let's assume that it fires these rockets for 10 seconds. T equals 10 seconds, obviously not a vector. And the question is, after that 10 seconds, what is the new velocity of the Enterprise? Well, I would start this off just like every other kinematics problem I've started off. Well, actually I already did. I drew a diagram, I labeled the diagram. Here's my initial velocity vector, here's my acceleration vector, my time. I want to know my final velocity vector. And I would look at these and I would say, all right, well, I have all the pieces I need to use the equation V equals V naught plus A times T. I have all of those pieces. And say, all right, well, let me put them to use. V is some unknown final vector. And here, there are two different ways to approach this problem. I guess actually, before I draw this, let me say there are two major ways to approach this problem. I'm about to show you the first one in this video and then the second one in the next video. Either one works. Neither one really requires any more or fewer steps most of the time. It's really just whatever you're comfortable with doing. So here's the first very common way to solve it. V, and now I just start putting in all of my other pieces as the vector components I have up here. My initial velocity vector is 30 I hat plus 40 j hat, and I'm just going to put parentheses there, even though I don't need them, but that's a good way to kind of keep my things separated, make sure I know what's what. Plus my acceleration vector, I'm going to move this out of the way. My acceleration vector is negative 2 I hat plus 2 j hat. Now here, having the parentheses is very useful because it reminds me that when I multiply by t, which is 10 in this case, I'm not just multiplying the last term by 10. T is being multiplied by the acceleration vector. This whole thing is the acceleration vector, and so the whole thing needs to be multiplied by 10. And so when I go to solve this, here's 30 I hat plus 40 j hat. And then over here, I distribute the t to every term. That's what happens when you multiply by the sum of something in parentheses. So I get negative 2 times 10, which is negative 20 I hat, and then 2 times 10 plus 20 j hat. And now I can just combine the like terms. I can combine the I hat pieces to get a final I component, and ditto with the j pieces. And so my final velocity vector, after this much acceleration for this much time, starting from this initial velocity vector, is 30 plus negative 20 I hat. So 30 minus 20 is 10 I hat. And then 40 plus 20 is 60 j hat. Meters per second, assuming the other things are meters per second, which I should have specified, but I didn't. And there we go. So you can see this was no harder to do in terms of the physics than what we've looked at before. Identify an initial velocity vector, an acceleration vector, and a time. Identify what we're looking for, the final velocity. Identify the proper equation, and then just plug in and use it. It just so happened that each of my pieces had 2 different components, but that's fine. I just did the math I would have done anyway, and just end up with 2 different components. Now, in the next video, we'll take a look at the other very, very common way to handle this whole problem.